Hello. All. So today we are going to learn about decision trees. Why do we need decision tree? How do we construct them? And what are the use cases? So first question that comes to mind is why do we use decision trees and how it works? So the goal of decision tree is really simple. It is to create a training model that can use to predict the class or value of target variable by learning simple decision rules inferred from prior data. So in simple words, we can say that it provides an effective method of decision making because they clearly lay out problems so that all options can be challenged, and it allows us to analyze fully possible consequences of a decision. So whenever we want to make a decision, the decision tree allows us to see all the consequences that this decision can lead to. So the best definition as given by the professor is here that a decision tree is a set of training examples. A set of training examples is broken down into smaller and smaller subsets, while at the same time an associated decision tree is incrementally developed. So basically the idea is we have a root node, and then we are getting smaller and smaller subsets of the root node, and then we further divide it into smaller and smaller subsets to find the correct decision. So this is how it increases incrementally as we go on dividing it into smaller subsets. And at the end of this learning process, the decision tree covering the training set is written. So entire training set gets converted into a decision tree. Decision tree can be used to build both classification and regression models. Now let's look at the data set which we are going to use for this entire PPT. The first thing which we are going to use is like this 4 predictor columns. That is nothing but outlook, temperature, humidity, and windy. And our target variable is hours played. So this is what we want to predict. Here this is our training data. So we are given the values on which we'll train our model, and hence we'll use this training data to predict in the future the hours played value. Before diving deep into the maths behind decision tree, let's just analyze this data so that it becomes easier for us to understand. The first thing which we are going to look at is the outlook. Outlook has 3 possible values, that is rainy, overcast, and sunny. Temperature is hot, mild, and cold. Humidity is high and normal, and windy is Boolean, that is true and false. Moving ahead, decision tree regression. Let's look at the regression model. So this is how a decision tree looks, and we'll see how this is constructed. But the only things which we need to know right now is that the first node is nothing but the root node. All the outcomes of root node are known as branches. All the elements are known as nodes, and the end node is known as a leaf. So let's move ahead and understand the decision trees used in different models. So decision tree, as you all know, are used in classification and regression model. In classification model, we further find the entropy, and we do the chi-square test. So I'll just give you a brief about what is entropy and chi-square test. So entropy measures the expected amount of information conveyed by identifying the outcome of a random trial. So a simple example is this implies that casting a die has higher entropy than tossing a coin, because each outcome of die toss has smaller probability than coin toss. So basically that is where we use entropy. And in chi-square test, we use it for hypothesis testing. The basic idea behind chi-square test is to compare the observed value in your data is matching to the expected value. So basically it proves that we accept or reject the null hypothesis. And again, in the regression model, we just need to find the standard deviation. Standard deviation is nothing but it tells us that it's a measure of the amount of variation or dispersion of a set of values So it basically tells us how far our value is from the mean in this data. Moving ahead. So now we are going to dive deep into the maths behind decision tree. So there are three statistical values for that, basically three statistical values which are used to generate a decision tree. The first is the standard deviation, which is used for tree building and branching. Next is the coefficient of variance, which helps us decide when to stop branching, and basically goes to the leaf node. And average is the value of leaf node. So these three statistical values are used in constructing decision tree, and we'll see how we are going to construct a decision tree from this. So let's look at the first column, that is the outlook, and with the target column, that is arts played. So we are going to find all these values for all the possible divisions of outlook, that is the overcast, rainy, and sunny. And we are going to find count, average, standard deviation, and coefficient of variance for all of these three categories. And after finding that, we'll get to weighted standard deviation. Weighted standard deviation is nothing but it tells us, it applies a weight or relative significance to each value in the set of value. So basically, higher the weights, that particular element is considered as more significant, or value is considered as more significant. So now we are going to find the weighted average. So we have the standard deviations from the previous slide, and now we are going to get the count, and using the formula of probability of sunny and standard deviation of sunny with overcast and rainy, we're just going to do summation of all three, and we get the weighted standard deviation. Again, we do the same for temperature and the target variable. We find everything, and then we have all the standard deviations here, and then we just plug it in the weighted standard deviation formula and get the final standard deviation. After that, we do it for humidity, the same process, and get its weighted standard deviation. And same for windy, we get the weighted standard deviation. It is just a Boolean, true or false. After that, we find the standard deviation reduction. So why do we need standard deviation reduction? So standard deviation is used to calculate homogeneity. Standard deviation reduction is standard deviation of target variable subtracted from standard deviation of predictors. So higher the standard deviation reduction means more homogeneity in data, and that will help to identify predictor variable for splits. So this will help us, this will help in splitting of data in the decision tree. So this is the basic formula for, let's say, two variables. The standard deviation reduction for two variables is given as SDR t, x is SDR of SD of t and SD of tx. So let's say we want to find the standard deviation reduction for hours played and outlook. So it would be standard deviation of hours played subtracted from the standard deviation of hours played, outlook. And all these values were calculated in the previous slides, and we just plug it in and we get 1.66. So as you can see that the standard deviation reduction is less here. And so the standard deviation reduction is less, so there may be less homogeneity. Moving ahead, let's check further. So let's find standard deviation reduction for each and every possible columns. So outlook, we get 1.66. For temperature, we get 0.48. For humidity, we get 0.45. And for SDR, we get 0.46. for windy, we get 0.28. So basically, this is the lowest standard deviation that we got. Okay, moving ahead, we see that now we can split the outlook because it had the highest SDR. So highest SDR was 1.66, and that helped us identify that we can do a split on outlook, and we get sunny, overcast, and rainy. So basically, the higher the standard deviation reduction, we do the splitting on that node. Now, then we do data partitioning of outlook. So these are the 5 columns of sunny, 5 tuples of sunny, rainy, and overcast. So we divide the data into 3 parts. After that, we look into each and every subsection. So outlook, sunny. So we calculate the standard deviation, average, and coefficient of variance, which we already had. And now we'll calculate it with respect to other columns that we have. So that is nothing but temperature, humidity, and windy. And the standard deviation reduction we get is 0.678, 0.370, and 7.62. Okay, so after this, after getting the sunny and calculating all the other standard deviation reduction, we find that the maximum we get is in windy, and hence we'll split the sunny in with windy, and then we analyze that particular data set. So here is the split. As you can see that we have split it with windy, and there are only two values, true and false, and here are the values of 47 and 26.5. So we cannot further divide the decision tree because this is the last node in sunny, and we do not have any further nodes on which we can split. Hence, this becomes our leaf node. After that, we do again the data partitioning, and we look into overcast. So as we have already looked into sunny, now we go to overcast, and we see that overcast, the lowest value and the highest value, there is not much difference. Hence, we do not divide it further into subcategories, that is high, normal, or hot, cold. Hence, there is not enough variance. So we directly just plug the average, that is the mean, in the leaf node of overcast. Again, we see the data partitioning of rainy, as we have already seen for sunny. So rainy is left, we go into rainy. And in rainy, again, we get the column of all the three columns of rainy. So rainy had temperature, humidity, and windy, which has the value of these are the temperature, humidity, and windy. And we also had the training data, that is the target variable. And we calculate the standard deviation, average, and coefficient of variance. As you can see, the coefficient of variance is high. So we'll further classify it into each and every category inside rainy. So rainy can be divided into temperature, humidity, and windy. And the standard deviation reduction that we get from all three is 4.18, 3.32, and 0.82. And the highest we get is 4.18. And hence we divide our decision tree of rainy into temperature, and temperature into cool, hot, mild, and we just plug the means of all the three categories. We cannot divide it further, hence this becomes our leaf node. Going ahead, there are some issues with the decision tree. I hope the construction of decision tree is clear now, and we are diving into the issues with the decision tree. So issues are missing values because we are always pruning the branches, and we do not consider each and every variable. So always there are going to be missing values. There are sometimes going to be numerical attributes. Sometimes we are going to overfit, or we are going to do some pruning. So we are going to try to satisfy a particular target variable, and for satisfying that condition, sometimes we might overfit the data, and that is one of the major issue of decision tree. And super attribute is something with many values. So let us understand each and every issue in detail. So the first issue is missing value. So for the numerical attribute, replace the missing value with let's say average and median. And for the categorical value, replace the missing values with most common value or most common value at node K, or just having the missing value as another branch on the tree. So we can make it as another branch. So these are the remedies which we can use for missing value, and we can just replace the missing value if numerical with this, categorical with this two, or you can just make another branch. Moving ahead, we have another criteria in decision tree, that is binning or decretization methods. So it is basically nothing but we divide the data into equal widths or into equal frequency, or we just take the floor function of log of x. So what is equal width? So the original range of values is divided into n intervals. So basically it would be 0 to 10, 10 to 20 with the same range. So as you can see, the range is same, it is 10 and 10, or with equal frequency. So strategy creates a set of n intervals with the same number of elements. So the difference between these two is, here in 0 to 10, there can be 5 elements, and in 10 to 20, there can be 10 elements. But in equal frequency, if we are dividing it into 0 to 10 and 10 to 20, both should have equal number of elements. So it should be 10 and 10. So these are the two categories which you can divide your data into, or you can use the function of log of x. That will do the same thing. So let's check the numerical attributes equal with binning. As you can see, I'm dividing temperature column into different bits. So here, as you can see, 85 falls under 80 to 90, 80 falls under 80 to 90, 83 same, 70 falls under 70 to 80. So we just give bins for each of the values, and then we just use bins to divide temperature into further categories. So as you can see, before we were not able to divide temperature, numerical temperature, into different categories because we would have to consider each and every value in the column. But now after binning, we just have 3 tuples which we need to consider, and we can calculate the standard deviation reduction as for those 3 values, similar to as we did before. So we do standard deviation, average, coefficient of variance, and count, and plug everything here. So instead, now we just have the bins here instead of variables. So we plug, it is the same way, and we get the standard value reduction at 0.48. Moving ahead, the other problem as we saw was overfitting. Overfitting, when a learning algorithm continues to develop hypothesis that reduces training set error at the cost of an increased test set error. So overfitting is when we develop the hypothesis that reduces training set error. So we are trying to reduce training error, but it in turn increases the testing data error. So this is known as overfitting's basic definition, and we avoid overfitting pruning. We avoid overfitting pruning basically. So we can avoid overfitting by pruning. So coefficient of variation, variance is, let's say the threshold should be 10%, and minimum number of cases, the count at each node is example 2. So this is how we can set the parameters of pruning, and in this we can avoid overfitting of the data, because our decision tree, if let's say the node has variance more than 10%, let's say it is 15, then it will just prune that branch and it will not move further, and decision tree won't be constructed after that, and hence we avoid overfitting. And next issue was super attributes. So like information grain in classification tree, like SDR is biased towards attributes that have large number of values over attributes which have small numbers of values. As we see that if an attribute have more data or large number of values, our standard deviation would be biased towards that rather than small number of values. So these super attributes will easily be selected as the root, and result is a broad tree that predicts perfectly using training data but performs poorly on unseen instance. We can penalize attributes with large numbers of value by using an alternative method for attribute selection using split function. So this is nothing but it is saying that we can we can make the super attributes as roots, and then we can use the split function and divide the data into smaller and smaller categories so that our SDR is not biased towards the larger value and it is equally distributed. And the split function is nothing but, as you can see here, that split of R split and outlook is given by this formula, which is minus 4 by 14 into log base 2 of 4 by 14, and this is nothing but the split function is given as split of t comma x is equals to negative summation of all x belonging to the data set, finding the probability of x and the log base 2 probability of x. So using this formula, some summation of or negative summation of all the values inside the data set, we find the split of R split and outlook, and just plug the values of T of x being 4 by 14, 5 by 14, and 5 by 14 again, as you can see here, and it gives us 1.58. So now we can look into the SDR adjusted. SDR adjusted is nothing but that we find the SDR of each and every column. So for now, we are looking into outlook. Outlook is divided into overcast, rainy, and sunny. So the standard deviation reduction comes to 1.66, and the SDR adjusted can be computed as SDR of the two variables we are looking and split of the two variables, that comes to 1.05. And lastly, we are just looking at the super attributes. The super attributes, as we all know, are easily selected as root, resulted in broad tree that classify perfectly but performs poorly on unseen instance. And we can penalize attributes with large number of values by using an alternative method for attribute selection referred to as gain ratio. So we can use gain ratio as well to penalize this attribute, which is nothing but gain by split. So which can be used to penalize this, and there is a great reference given on professor's website for gain ratio. I will highly recommend to go there and learn about it. So here we are just using the super attribute as you can see, the super attribute is ID now, and we are just calculating SDR of R split with ID, which comes to 9.32. Split comes to 9.97, and SDR adjusted comes to 0.94. So SDR and split is high, so we will keep the super attribute ID at the root node and divide our decision tree further. That is the end of decision tree construction. I hope this was informative. Thank you.